In today's video, we are going to explore the different types of elasticity, clearly explain important concepts such as spring constant and Hooke's law, and finally examine how force and extension are related using graphs. When a force is applied to an object, it can cause the object to undergo compression, stretching, or bending. This is most easily seen in something like a spring, but the principle also applies to a wide variety of other objects, including things like balls or mobile phones. These other objects might not be as visibly elastic, so the changes in their shape might be harder to notice, but the underlying concept remains the same. No matter what object we are examining, we need to apply more than one force if we want the object to remain stationary while being deformed. If only a single force is applied, the object would simply move in the direction of that force. For instance, even when you press down on an object against the floor and think you are only applying one force, the floor is actually pushing back with an equal and opposite force, which means there are still two forces acting. When an object does change shape due to applied forces, we say that the object has been deformed. There are two main types of deformation that you need to be familiar with, namely elastic deformation and inelastic deformation. If the object goes back to its original shape once the forces are removed, we refer to this as elastic deformation, much like an elastic band that returns to its normal shape after being stretched. On the other hand, if the object does not completely return to its original form and stays changed in some way, then this is known as inelastic deformation, or sometimes called plastic deformation, similar to how plastic can be molded and then retain that new shape. A key concept to understand next is extension, which refers to the increase in length of a spring or similar object when it is stretched. For example, if we suspend a spring from a solid support and add weights or downward forces to its lower end, we can observe how its length increases. Even before we add any external mass, the spring's own weight will exert a downward force, creating some initial extension. This initial length change caused by the spring's weight is usually very small and often considered negligible, so we typically treat the entire unstretched length as its natural length. When a mass is added to the spring's bottom, the additional weight pulls downward, causing the spring to stretch further. This extra stretch is measured as the extension. Importantly, the solid support holding the spring also applies an equal and opposite upward force, which is why the spring remains suspended instead of falling. As we gradually increase the force acting on the spring, such as by adding more mass, the extension also increases. This relationship is proportional, which we can describe with the phrase force is proportional to extension. In symbolic terms, this can be written as force is proportional to extension, where force is denoted by the letter F and extension is usually represented by the letter E, though it is sometimes written as X instead. The amount a spring extends under a given force depends on a property known as the spring constant, represented by the letter K. When we include this constant in our proportionality expression, we arrive at the formula force equals spring constant multiplied by extension. The spring constant is measured in newtons per meter, and the extension is measured in meters. The spring constant tells us how much force in newtons is needed to stretch the spring by 1 meter. The larger the spring constant, the stiffer the spring or material, meaning it takes more force to stretch it. We can visually represent this relationship by plotting a graph of force on the vertical axis against extension on the horizontal axis. As the applied force increases, the extension increases too. If the graph is a straight line that passes through the origin, we can conclude that force and extension are directly proportional. This is what we refer to as Hooke's law. While this proportional relationship holds, all of the deformation experienced by the object is elastic, which means that the object will return to its original shape once the applied force is removed. However, there is a limit to how far this law can be applied. Eventually, the graph will stop being a straight line and begin to curve. The point at which this occurs is called the elastic limit or the limit of proportionality. Beyond this point, Hooke's law no longer applies and the material may not return to its original shape, meaning it has undergone inelastic or plastic deformation. That brings us to the end of this explanation. We hope that this video has helped you gain a clearer understanding of elasticity, Hooke's law, spring constants, and force extension graphs. If you found it helpful, be sure to check out our other content, and we look forward to seeing you in a future video soon.